So now let's take a look at an example of executing programs on a computer. So before we get into that, let's figure out what's inside a computer. So here's my list. You've got a processor or CPU, and here's the processor. You're looking at the bottom of it. All these little bumps here, these are the pins that connect the power to the processor and have the data that come in and out. All these little things here, these are capacitors which try and keep the voltage constant in the processor. You have memory, random access memory or DRAM. These are all chips that have lots and lots of data stored in them. You can see they're arranged together to make more data across. You have input-output, so keyboard, network, mouse, and you have some sort of storage. So typically a hard disk, which is a spinning chunk of metal that uses a magnet, or you can have flash memory, which looks a lot more like this and just has a different way of storing data. So let's take a look at how the computer system is built up with those components. So we have the central processor, or the CPU. We have memory, which is DRAM, dynamic random access memory. We have our input-output controller, and this is connected to things like our storage, either flash memory or hard disk, our user interface, keyboard and mouse, and a display. And now let's go see how these connections are. How big are they? So between memory and a central processor, we have a connection somewhere between 30 and 50 gigabytes per second, so 32,000 megabytes per second. A much slower connection to the input-output controller over here, and if you look at the connection to the storage, so a hard disk, it's only 750 megabytes. So these are to scale. So this is how much faster you can access memory compared to how fast you can access a disk. USB to access the keyboard and mouse is even slower. And displays, well, you got to update all the stuff on the display, but it's not that fast. Now the display isn't connected to these things. Instead, the display is connected to a separate processor. So this is the graphics processor, and this is the central processor, so CPU and GPU. And the graphics processor is connected up to the I/O bridge over PCIe, and that's about 5,000 megabytes per second. So what you see from this picture here is you see that the central processor can connect to the memory very, very fast, and everything else much more slowly. In particular, when we get to the hard disk, enormously more slowly. And we'll see the impacts of this later when we talk about I/O and virtual memory. So let's take a look inside the processor. So inside the processor you have a part which does the computation. This is the addition, subtraction, or multiplication, the part that actually computes. It's often known as an ALU, or arithmetic logic unit. We also have data registers. This is a small and fast memory that holds just the things the processor is working on at that time. So in the example we'll look at here, it's just going to have 2 entries. These two connect together so that if you want to do addition or subtraction, you're going to take data from the data registers and compute on it. We also have control logic. The control logic is responsible for making sure that everything over here knows what it's going to do. So it tells the compute unit what operation to do. It tells the data registers which register should you use. And in order to know what instruction to do, we need some way to store the current instruction. So the current instruction is going to go into the control logic. The control logic is then going to use the current instruction to tell us which data to access and which operation to do. Now in addition to that, we need to be able to access our memory. This is where we keep most of our data, and this is big and slow. So we have lots more entries in our memory than we do in our registers, but it takes a lot longer to access them. And of course we need some way to read the instruction so we can get the current instruction, because our program is going to be in memory, and the data registers need some way to read and write data back and forth. So we've got most of the stuff here, but we're missing something. And let's take a look at a program to see what we're missing. So say I have this program, while I does not equal 2, I equals I plus 1. So this is going to go around in a loop, incrementing I until it equals 2. So from this program, how do we do this if I does not equal 2 part? How do we control that? So the part that we're missing here is we need some way for the compute to tell the control which instruction it should do next. So the compute needs some way to say, hey, I equals 2, so now control, you can go and choose a different next instruction. So when we've got this, we've got the ability for compute to decide if we should do the loop again or keep going. Can tell the control chooses the next instruction. We go and load the instruction from memory. That instruction then tells the control what to do. The control tells the compute what to do and their data what to use, and it computes the next value. So that's what we have in our processor: memory, control, and compute. Now let's take a look at how we program the processor. So here's a C program, we saw it before. While I does not equal 2, I equals I plus 1. When you want to run this, you run it through a compiler. The compiler generates this assembly code, which tells the computer which instructions to do. This gets loaded by the operating system into the memory and then gets executed from there. Now let's take a look at what the compiler did to translate this program into this assembly code. So here's the first instruction we're going to look at, I equals I plus 1. So what did the compiler do? Well, that's over here. It turned into R0 equals R0 plus 1. So the compiler put our variable I in register 0. So R0 is where I is, and it says, okay, go ahead and add 1 to R0. So this is the same thing as this instruction, but now the compiler's decided that I is going to be stored in register 0. Let's look at this part over here, while I does not equal 2. So that's this part over here. So look at what's happening here. In this instruction, we do R0 minus 2. Remember, R0 is I, so we're subtracting 2 from I, putting that in R1, and then we're doing jump 0 R1. So we're checking if the result is 0. So how do we check if I is not equal to? Well, we're checking if I equals 2 by subtracting 2, and if it does equal 2, then we're done. So that means we're going to do this thing while it's not equal to, and then when it does equal to, we're going to leave. So when I does equal to, we jump down here to done. Okay? So this is the part here that checks should we exit the loop. How do we go around the loop? Well, look down here. If we don't go out of the loop, that means I does not equal to, then we get down to this jump instruction, which brings us back up to the top of the loop. So we're going to go through the loop, around and around, until I equals 2, and when I equals 2, we're going to leave the loop. And so that's going to do exactly what our code has over here. While I does not equal 2, we're going to go through the loop.